Let's look at the concept of the impedance and admittance. And the impedance is just a more generalized idea, concept of the resistance, right? The resistance only applicable to the time domain, or if you only have resistors, right? So if you have inductors and capacitors, as we said, we saw these terms, and Ls and the C and the CS, right? 1 over CS. So these are the impedance in the S domain. If you remember the impedance in the phasor, right? In that case, we have the J omega L, and we have 1 over J omega C. So you basically, if you replace S by J omega, and then you get the impedance of the inductance and the capacitance in the phasor, right? So therefore, the S domain is more generalized, even more generalized than the impedance concept in phasors, right? As we said, because the limitation in terms of phasors are sinusoidal, steady state. These two things have been removed, right? These have been removed, and we can use this to solve more general circuits, or at least with more general input conditions. And as similar to the admittance in the phasors, and admittance Y is just equal the 1 over ZS, right? So therefore, for the resistance, the admittance would be, so admittance is more similar to the conductance. So let's see if the resistance and the current is proportional to the admittance, and inversely proportional to the impedance, things like that, right? So the Y sub R for the resistance is just 1 over R, right? So this is the Y sub Ls, this is 1 over Z sub Ls, right? So in this case, this equal 1 over Z sub Cs, and that's the reason for, actually this is the reason for some of you asked, and then negative J 1 over omega C, because the impedance in the phasor for the capacitor always have a negative real parts, because 1 over J is equal negative J, right? So that's the concept. Let's look at a simple example and how to utilize the things we discussed to solve a basic circuit. We're gonna solve more complicated circuit in this chapter, because this chapter is basically working the methods for solving circuits in S domain itself, because we know how to transform the time domain signal to the S domain, and we also know how to go back to the time domain by inverse Laplace transform, right? So we have 2 lectures for each. And let's look at this circuit here. The case we're going to transform everything to the Laplace domain. So in this case, the resistance to Laplace domain, nothing changed, right? So the Vs, we're going to use capital Vs as a function of S. So this is Laplace transform of V sub St. And then for the inductance, we can use either of these equivalent circuit. We can use, let's see, if I use this one here, and this is going to be the impedance, right? So this is Z sub Ls, that's going to be equal L times S. And this term here is going to be equal L I sub 0, I 0. So this is the initial condition, right? So that's the voltage. Let's see the current here. This current we're trying to find, that's going to be I sub S, and the current across the inductance V sub Lt. Make sure you are using the total voltage V sub Ls to correspond to that time domain signal, right? Not just the across that impedance, because that we call V sub L prime, that does not include the initial condition, and that's not correct if you do the inverse Laplace transform to get a V sub Lt from that V sub Ls. Okay, so in this case we have v sub s that's equal to the Laplace transform of v sub st, and this one is fairly easy, so we have 10 over s, right? So 10 times ut is the Laplace transform is just 1 over s, and z sub l s is ls, and l is 0.001 s. And I0, so that's the Li0, that's equal 0.001 times 2, that's 0.002, right? And so in this case, we're gonna first, let's say, find I sub s, is. So is is gonna be equal to vs plus v sub l times I0 divided by these two impedances, so this is R, or z sub r if you want to call that, that's fine, plus z sub ls, and in this case we got 10 over s plus 0.002 divided by 1 ohm, right, plus 0.001 s. And if you calculate this, this will end up with 2s. So if you multiply 1000 s on both numerator and denominator, I got a 2s plus 10 to the times s plus 1000. If you do the partial fraction expansion, you can get this in two terms that are going to be equal to 10 over s minus 8 over s plus 1000. Right, so therefore the it, do the inverse Laplace transform with it, and this is going to be equal to the inverse Laplace transform of I sub s, and that's going to be equal 10 minus 8 times e to minus 1000t times ut. And the unit for this one should be amps. Right, so that's for the current. And let's see the voltage here, the V sub Ls. So the V sub Ls is going to be the voltage across this minus I0, right? So in this case, this voltage here is going to be I sub s, is times this the impedance. So the VLS is going to be equal Ls times the is. So that's the V sub prime, V sub L prime at time plus L times I0. In this case, that's going to be equal to Ls, which is 0.001 s times 10 over s minus 8 over s plus 1000, and plus Li0. Li0, that's 0.002. And minus here should be, because that the plus minus sign is flipped. So if we work on the numbers, 800 over s plus 1000, right? So no, that's 8. Sorry. It's 8 times, yes. So that's so 8.88 times 1000, that's 8. So this is the Laplace transform, and the inverse V sub Lt, that's e to minus 1000t, and ut, and the unit volts. Okay, that will concludes the that will conclude the third video clip. and we're going to talk about the KCL and KVL.